Good morning, class. Let us begin the class. This is what we have last week. We simulate the car, on Simulink. But then the simulation focus on the control system itself. Okay. Uh, so we built this block diagram in Simulink. Remember? So we try that using Simulink, you can simulate a control system of any kind of mechanical system, so long that you have the transfer function that you put as the plan, and also you have a controller that can work to minimize the error. And we also have proof that using the simulation itself, we don't have to know the mass of the car, and we don't have to know the value of a constant. Okay, that is the specialty of the control system itself. And then we also learn about the simulation setting in the Simulink, where you can put any variables you put in the callbacks. And then I also teach you on setting the step size. Did you check the step size of your simulation? If your step size you leave it auto, then the system will set a very large step size, and then your simulation result usually is not smooth. Okay, before we go into the new topic, I want to discuss about the analytical solution. Okay, how do we get the traction so that the final velocity is equal to our desired velocity? So we are not going to use the Simulink in here, but rather we are using the differential equation itself. Okay, so we start with the differential equation built from the Newton's law. We are not converting it into Laplace, but then we just expand the equation here. You see, we have the traction equal to m v dot, and then we assume c to be 0. In this case, we assume c to be 0. And then after that, what we do here is that we express v dot. Okay, what is v dot in here? V dot, we just move m to the left side, so m becomes the denominator. Okay, and so we have a new differential equation in v. Usually differential equation have a term on the homogeneous part, but then this one, the homogeneous part is 0, so we only have the particular part in here, that is the extra input coming to the system. So the question is that how to choose the traction t so that our desirable steady state velocity to be v star. Let's say v star is the desired velocity. How to do that? Do you sit too far from the? You want to sit there? You are seeing like this, right? Yeah. Okay. The strategy in here is that we create a new variable, which is the velocity error. Okay. The velocity error is defined as the current velocity minus the desired velocity, and then we just expand the dynamics of it. So what we do is that in here we put the dot on the top. Okay, we take the time derivative from here, but because v star is a constant, so the time derivative of v star is just 0. Okay, so because v dot is equal to the v dot, and then v dot is just that one, so we move the 1 over m times t to here. Okay. And then based on this, we know that the error, we want to make the error to be 0, right? And because this is a differential equation, As we discussed several times, when we have a first order differential equation, are you taking differential equation now? Next semester. The solution for the differential equation for the first order, if we have VE dot, then this will be the solution. If the term on the right is in V, in VE. So how to force this equation so that it has this solution is that we make the traction to be this minus K times VE. Some people may say, you are cheating. Is this considered cheating? No, it is not cheating, but you can say that you are being tricked. You are tricked because initially we are thinking of how to set the t so that final velocity is the desired one, but we just have to make the traction to be a function of the error itself. So we make the traction to be proportional to our error. Okay, if the error is large, then the traction is large. When the error is small, traction becomes smaller. And so we finally get this equation, so we get the same solution that we want. Okay, so this solution is in the continuous time solution. Why is that? At continuous time we have the dv over dt in there. But I want to bring you into the discrete time solution now. So we want to discretize this, make it into a discrete time equation. Okay, now it comes the discrete time equation, where we can work on it using MATLAB's loop. Do you learn loop equation? Making loop codes in MATLAB in last semester, you learn. Yeah, we can take advantage of that. So you see here, the v dot is we can express the v dot as the subtraction of the future velocity minus the current velocity, and we divide it by the time step. Okay, so this is just the gradient of the velocity itself. Anyone get an idea how does it come like that? You get the idea? You get the feeling? Not yet? No, not yet. Let's say if your velocity is going like this, going that way, okay, and then the time that we have here, now it becomes a discrete time, not a continuous time. By the way, do you know what's the difference between discrete and continuous? Have you ever heard discrete graphics card? You don't know? Integrated graphics card. Yeah. You have integrated, and the other opposite is discrete graphics card. What's your graphics card? Integrated. Integrated is bad. Performance is bad. The better one is the discrete time.
You just learned that recently.
Oh, recently? Oh, okay.
I don't know anything about computers.
Oh, okay.
That's lucky.
So the difference is that when the time is continuous, then the value of your function is available at any time. Let's say from 0 to 10 seconds. You mention one particular time. What's your choice? 5. Okay, it is available at 5 seconds. What else? 5.11. Okay, it is also available. Any other choice? No. Between 0 to 10. Just choose any number. 5 is there already. Pi. Oh, pi is here. Okay, pi is there. It is available. Yeah, because continuous time, we don't have any limit on how many decimals that we can place. That is continuous time. Okay. However, with a discrete time, we are using index. Okay. So in here, I will draw same one, but then we put an index. Let's say this is I. Okay. 1, 2, 3, 4. So it is an integer. Yeah, between 1 and 2 we don't have data. We only have it here, we have here, we have there. Okay. Yeah, actually with this discrete, then it's like this. But in MATLAB, they interpolate it so that it becomes a straight line in here, straight. Yeah. So between 1 and 2, this is our delta t. Yeah, the step time. The delta t. Okay. So what if I want to obtain the slope in here? Let's say I want to get this slope. How do I get the slope? Yeah, I'm getting this m divided by this delta t. Yeah. So that one divided by this one, I will get the slope. And exactly this m is equal to velocity at 2 minus velocity at 1. Yeah. I divide by delta t. And this slope is the same as the time derivative of the velocity itself. Okay, because the dv over dt itself, yeah, this is the slope of vt at t. Okay, so which is why we are using that formulation over there. So how do you adjust the delta t? Yeah, it really depends on your computation. Okay, computation power lah, and how many data that you want to have. It really depends on that. So we are trying to use this formulation to get the time derivative of the velocity. Okay. So vi plus 1, it will be the future velocity. Vi is the current one. Delta t is the time step. Okay. I will start from here, continuing the continuous time system. And then once I get the v dot, I will express the v dot as this one. Okay. So vi plus 1 minus vi divided by delta t. And then I get the expression of what will be my future velocity. Do you remember the kinematics equation? The Vt is equal to V0 plus At. So this one over here is the At itself. Okay. Yeah, related, yeah, the physics one. Okay. Yeah, I also write it here. Now, what's your idea? If I want my future velocity to be v star, how do I set the t in here? This is just simple algebraic manipulation. If I want my vi plus 1 to be v star, what do I need to do? How do we set the ti? If I want my future velocity to be v star, how do we set the traction ti? Huh? I wrote it here already, right? Yeah. Why are you so bengong? Bengong. What? So we just decided like this. This will be our traction. Okay. If I set the traction to be like that, then my future velocity is guaranteed to be the v star. Agree with me? Yeah. So this is the codes that we can write on MATLAB based on this. Okay, let us define the mass first and then the delta t. Delta t, let's say 0.1. I put k equal to 1. K, I will use k here. And then this is the desired velocity. And if I want to use the loop, then I have to define my first value of the v. Okay, so you check here, I'm using if condition, so after else I have to use n here. Sorry, my if condition is that if my velocity is not the same with the desired one, then I will use this formula for my traction. If it is the same, then the traction is just 0. Okay, and then after that I write down this equation in here, and I will let MATLAB to update it. Can you try this in your M file? You write down M file codes. Is it working or not? We have to put n over there, yeah. N. Let me write down n. Okay, you try. Any question on this? Understandable, yeah? This one? Yeah. This IN you can set 100. Just set it 100. I use M file Marco. Don't use the command window. Are you using M file? Not yet. Don't forget to put the semicolon after the TI, okay? Yeah, put semicolon. I forgot to put the semicolon. Any problem? Not clear. I don't think it is clear. You can see it? Oh, so narrow. Huh? Which one? Yeah, first M.
And
Hmm? Yeah. Yes. Yes. Yep. You haven't defined the IN. You put 100 lah. IN 100. Okay. Yeah. Now you can check the velocity. Maybe you can plot the VI. Plot V. Just plot the V. Yep. Yep. Like that. Okay. Very steep, right? Yeah. But then, yeah, after one time step, the velocity becomes the desired velocity after one time step. Anyone succeed? Ah, TNV. You said IN first. IN. What is IN? And then what's the problem? Line 9. Oh, this one you don't have the dot. No need the dot. No need dot. Just like that. Yeah. Divide slash dt. Okay, try. Yeah, you put semicolon in here and in there. In here also semicolon. Yep. Okay, anyone get it correctly? You try to plot the velocity. What do you get? Plot the velocity. Wrong. What's wrong? Index exceed the number of element. Wait. What do you? This is V, not capital V. It's small V. Yeah, it works.
Title lo jadi komen dulu. Nama ini.
So uppercase and lowercase is important, yeah. Do you get it right? No, we are not plotting I and V. Just plot V. What do you get? Yep. Oh, sorry. Yeah. Anyone still have trouble? You try to plot the V. Yeah, straight away, in one time step, it becomes the desired velocity. You can try to change the desired velocity to 10. See what happens. Change to 10. Does it become 10 also, the velocity?
Intervalnya number of data.
Wah. Itu jadinya apa?
Yeah, we put the start.
Tadi pas videonya buat nggak pakai start. Tadi Tapi pas dikit kan.
Here, start here.
Bukan, M times VD.
Oh, okay. We have to multiply. Sorry. There is a star in here.
Tapi tadi pas VD-nya sama. Still not.
When VD is 1, it's not.
VD-nya sama. When VD is 1, it still runs.
Oh,
When VD changes, won't run.
well, I'm not sure what happened. That one. But we have to put the star in there. Yeah. Sorry about that. Yeah, MATLAB magic. We have to put the star. Okay, when you put VD equal to 10, does it still working? Working, yeah. All right. So what is our disadvantage here? The disadvantage here is that when we decide for the traction, do we need to know the mass of the car? Yes. So how do we remove that dependency? Huh? What's your idea? Let's say we don't know the mass of the car. How to do that? Yeah. Just plot V. You write down plot of V. It will just plot. Yeah, we haven't got into the point where you plot V versus time. Not yet. Okay. Okay, what's your idea? Any idea? We don't know the M. How to do this? What's your idea? Let's say we don't know the M. You remove M here. Remove. Try to remove, and then you change K to 10. Let's say change to 10 or 100 lah. Make K 100. Remove M in here. You try run it. Yeah. Now we just try. You try K to be 10, to be 100. See what happens. Just try. Yeah, the result is different, of course. What is the situation now? Bit like what? Let us see it.
Jokowi nggak ada sama sekali. Kosong.
Is that the situation?
Oh, here, right? Oh, Vista.
Wait.
Oh.
You made a mistake?
I remember.
Huh?
I remember.
Yeah. Okay, remove the M. What happened? Okay, now you change IN to be 1000. Huh? It shouldn't be like that. Yeah. So you should find the response to be like this. So it will approach the V star in the end, but then it has a slope, not very steep. What do we get now? Huh? What? No. Oh,
Tahu.
you put what is your k?
Dulu ya.
K is 1. No. For I from 1 to 100. Let's say 100.
Oh, begitu. Naik langsung lurus lah.
Oh,
Let me see.
iya. Tadi gua kayak gitu kan.
Mhm. You remove the M, right? You haven't removed the M.
Kasih kita aja.
No. You remove M from here.
Oh,
Yep.
oh, siap. Dan K.
K is 10. Let's say 10. Okay.
Oh, sekarang mau jadi error.
You start. You run it.
What the hell?
Yeah. Okay.
Ada.
So you increase again the I to 1000.
Lu yang gak konsisten.
Enggak, tadi gua 100 udah kayak gini.
Gua
Yep.
bener-bener gak ada kok.
So it needs more time to. Yeah. It needs more time. Okay.
Oh, kayaknya selalu 10 ya. Oh, kayaknya selalu 1 woy.
Enggak, nanti diganti.
Apa sih ini kan? Kok jadi error lagi sih?
Ya otak.
Yeah. If you don't get this kind of response, then you might make a mistake.
No, I tried it. Terus kan gue jadi aneh sih tadi udah aneh.
How is it?
Keren.
Nadia, you get it? Yeah, you increase the I from 1 to 1000. Increase K to 10.
You did it.
Okay. Yeah, like that. To remove that kind of behavior, you put semicolon. Yeah.
Apa lu mau ikutin pawak?
Okay.
Parah lu.
Lu ngetawain awalnya. Udah gue sih Pak, ada tanda kunci.
So this kind of curve is doable, yeah. More doable than the very steep one. More doable.
Ya benar.
Can anyone explain why this idea works? We don't need to know the M. Anyone know why this is working?
Headlock.
Hah? Yes. The adjustment is okay. So even if you set the K random, let's say you put the K random, eventually the V will reach the desired velocity. Okay. Okay ya. Yeah, M and C are unknown, then we do this just now we do it. The disturbance, let's say we have an unknown disturbance like this. I go with the Simulink, but you have Simulink right now? So you try to make an extension to your Simulink. That is, you put a summation in here, yeah, where this is coming the wind disturbance. Do you still have the Simulink file last week? Yeah, you can try.
Bisa hehe doang.
Mana dia cuma nggak bisa huruf vokal lain.
Apaan sih kalau udah tahu?
Naik.
So you should get this kind of behavior. Desired velocity. Legend.
No velocity itu apa ya? Step ya?
Apa?
Step ya?
Yeah.
Big step, little step.
When you put the disturbance in, you will find out that the velocity is not reaching the desired velocity. Yeah, because there is a disturbance. We put the disturbance as a step function in here. Yeah, and I put the step value to be 100, very high.
Cok ini aneh banget.
When disturbance itu apanya soalnya?
It is the drag force coming to the car.
Ya.
Itu bloknya saya lupa yang kayak
Ya apa?
yang kayak kurus gue itu. Ya.
Step.
Which one? This one, step.
Oh, step. Gue lupa namanya.
Do you have the last week? Oh yeah, you just copy and paste.
Oh iya.
Yes. Do you know that you can copy and paste the block? Let's say you want to duplicate it. You just double click and change the value.
Yang
Hah?
Yang example itu
Apa? Oh, sini. Areanya masih.
Itu kan kalau copy paste kayak misalnya kita set di stepnya set 10 gitu. Jadi kalau copy paste jadi awalnya kita 10 lagi.
Yeah. Yes.
Lanjut 10.
Let's say you copy paste this desired velocity.
Ya.
yang mana?
Okay. I copy and paste like this. Like that one, you mean?
Yeah, my question is the inside
Channel,
is it following that or is it
Yeah, following.
Oh, okay.
So you can just change the value. Oh, that is mux. MUX. Huh? Mux. We want to plot several chart on one scope. You use the mux. This one, MUX. Yeah, this one is mux. I'm using mux there so that I can compare the desired velocity and then the actual velocity. Are they matching or not?
Bisa aja orangnya.
Okay, are you successful in getting it? The scope, this one? Huh? This one? MUX. This one? Mux. MUX. You can find in the library. I'll show you in the library. You go into the signal routing. Signal routing, you find mux. Okay? Which one? With disturbance, you just put a final value. Yeah. Does it reach the desired velocity? Yeah, mine doesn't reach the desired velocity. Over. Okay, if I put my k to be 500, slower.
Final mana? Hah?
Wah. BM ini apa? Kok balik ya?
Nice inverse.
Hah?
Oke ya. Yeah, we have to tweak the controller. We have to tweak the controller.
Itu gimana?
It's a step input. Oh,
Oke-nya
yeah. In this example, I'm choosing 100 as the final value.
Oh, desired velocity.
Hah?
Desired velocity yang paling itu.
I'm just putting a value of 30.
oh.
Tapi
Berikutnya tadi.
kemarin
Tapi masalahnya kontrol satu per S ini.
coba panci jatuh.
Philip jangan marah Philip.
Kemarin kayak gimana ya? Kev, lu copy paste
Apa?
dari yang kemarin.
Enggak, gua pakai kemarin.
Gimana sih?
Yeah. Okay, later on in semester 7, you will learn on how to design this controller so that the desired velocity can still be achieved even when you have disturbance. Okay, but then you need to know on how to simulate it first. At least now you have your own laboratory in the MATLAB where you can try any kind of dynamic simulation. Okay. For next week, I want to go with this Euler method. Yeah.
Apa itu?
Just now we do it. Yeah, you are using the for loop. That one is the Euler method. It is when you express the x dot to be like this one. So this is the Euler method. Yeah. The idea is that you want to express what will be the future value of your variable.
Apa sih dari papanya apa itu?
Like this, okay, and then this x dot, it comes from your differential equation. Okay. For next week, I will give you a problem of simulating this using Euler method. I want to see how you solve it. Okay, you write down your formula to get the value of x. That will be the homework for next week.